Okay, so today we're going to do something that I think is pretty fun. We're going to talk about quantifiers. Now, you might ask yourself, what is a quantifier? Well, we're going to get there in a second. Let's just look at these sentences I already have written at the top. There is a natural number. There exists an integer. For every element in the set A, blah, blah, blah. Sentences, statements, claims just like that are probably starting to pop up, or maybe you're just starting to notice them a lot more in your math classes, right? And so, if these are statements that we're saying all the time, whether it's because it's in a theorem, or we're proving something, or we're just claiming something, I don't want to have to write it out every single time if I'm saying it so many times a day. I'd like to just write it in very easy to write symbols, shorten what I'm writing because we're here to do math, right? We're not here to write essays. Well, luckily for us, there are some symbols that are going to help us. We have an existential symbol and a universal symbol. So for claims like there is a natural number, there exists an integer, we're just talking about one singular object, we're going to use this little backwards E, right? That's our there exists or there is symbol, right? So to say there is a natural number, what I might write is there exists an X in the set of natural numbers. And there we go. Look at how short that sentence became, right? How about for the next thing? There exists an integer. Okay, well, I'll just say there exists an X in the set of integers, and that means there's an integer, right? So now what about our universal? Could you guess what that might be? It's going to be an upside down A. It's going to look just like this. That's our universal quantifier. So to write out the statement for every element in the set A, I would write for all X in A. Maybe I could have chose a better name for our set since our universal quantifier is an upside down A. It could have been anything. It could have been B. It could have been for all integers. We would have just wrote for all X in and then our symbol for integers, right? So that's some pretty easy stuff to deal with. And now what we're going to do is we're going to talk about proving these kinds of statements. And I mean, they're very straightforward when we start. So to prove existential statements, just give an explicit example. And then we want to show that X, our example, satisfies the claim we're making about it, right? So let's look at this example. There exists an X in the set of integers that is even. Okay, so my proof might look something like, let X equal 4. Clearly, okay, that's not how you spell clearly. Clearly, X is in the set of integers, right? Because 4 is an integer. And X is even, right? And I guess if you really wanted me to write out all the details, I could say because 4 is equal to 2 times 2, so it's divisible by 2, so it's even. But we don't have to waste our time with that with such a simple example. But there you go. My claim was there's an integer that is even. I said, okay, let X equal 4, and then I showed that it satisfies the claims I'm making. 4 is an integer, and it's even. And then we're done. So now, how do we prove universal statements? Well, for existential, we were specific. We gave an example. For universal, we're going to let X be any arbitrary element of a set, right? And then we'll show that X satisfies the claims. And the reason we're letting it be arbitrary is because if we can prove something about X when it's just arbitrary, it's just an element of the set, then when somebody tries to nitpick and disprove us and they choose some element in our set, that specific element will always work because we proved it arbitrarily, right? So let's do an example. Let A equal the set of integers such that 4 divides X. Okay. And now I'm claiming for all X in A, X is even. That kind of makes sense, right? You can picture that in your head. If something is divisible by 4, it's probably even, right? But let's prove it, okay? So let's start off by being arbitrary. Let's say let X be in A, right? Then 4 divides X. So, and now I'm going to use an exists thing, right? I'm going to say, so there exists a Y in the set of integers such that 4y is equal to x. Look at that. See, I didn't have to write out there exists this time. I just wrote the backwards e. So, okay, x is an a, 4 divides x, so there's an integer such that 4y is equal to x, right? Then I might say equivalently. Okay, I hope I spelled this right. That would be embarrassing. So equivalently, I could say 2 times 2y is equal to x. Clearly, oh my gosh, I can't spell, I'm a math major. Clearly, x is divisible, or I should just say clearly clearly 2 divides x is what I'll say. So x is even. Gosh, I just don't know how to write apparently. So x is even. And there we go. We proved our claim. We let x be arbitrary, just an element of A. And since it's an A, that meant that 4 divides it. So we knew that 2 times 2y is equal to x. So we showed that 2 divides x, so x is even, right? See how we got there logically? And now if anybody took some random element from the set A, say 16, because 4 divides 16, well, we know that 16 is even because we proved our statement for arbitrary x in A. Now, the next thing, and we're almost done here, I want to talk about is negating quantifiers, right? What if I negated an entire sentence? And so I negate my sentences, my claims, by using this little tilde in white next to our yellow and blue sentences, right? So let's say I had the claim, there exists an x and A, blah, 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 claims about x, and I negated it. What we do is we push that tilde through, right? We push that tilde to our claims about x, and when we push it through, what happens is we flip our quantifier and we negate our claims about x. So what this is going to become, we're going to flip our quantifier, so there exists, we're going to make it a for all statement, so we're going to say for all x in A, and then we're going to negate our claims, so we'll just negate and then claims about x. And I mean, you could probably already see at the bottom, we're going to have some examples, so if this isn't making sense yet, just hold on a second. And now we're going to do the same thing for our universal statement, right? So we're going to push the tilde through. We're going to flip our quantifier to a there exists x in A. And then we're going to negate our claims about x. So I have some claims down here, right? I claim that every person is happy, right? Now, that might or might not be true. That's not the point here, right? So our claim is every person is happy, and what I'm going to do is I'm going to negate it, right? Now, every person, that sounds universal, right? That sounds like for all people on the planet, people is happy, you know? So this is a universal statement. So if I'm going to negate a universal statement, I'm going to flip it, right? I'm going to make it a there exists, and I'm going to negate my claims. So instead, when I negate every person is happy, what I might say is there is a person, cannot write, there is a person who is unhappy, right? See that change I made? I went from every person to there is a person, there exists a person. In my original claim, people are happy, I negated and I said is unhappy. And that makes sense, right? If someone said every person is happy and you said that's not true, all you have to do is find a single person who is unhappy, right? Hopefully that makes some more sense. It's a little bit to digest with this whole quantifier business. So now I have another example. Someone is unhealthy. One, okay, so someone. That's probably it is an existential statement. It's just about one singular person. So there exists a person, and that person is unhealthy. So I'm going to negate that, right? And so our there exists becomes a for all, and our unhealthy, well, the negation of that I'm just going to say is healthy. So we go from someone is unhealthy, we negate that and we say, oh, I was going to do that wrong. So someone is unhealthy, we're negating that, we're going to say all people, or maybe I'll just say everyone, all people are healthy, right? And let's just like make sure that makes sense again. So if someone said someone is unhealthy and you were like, no, that's true, then you would have to follow up or prove that every person is healthy, right? If you were going to negate someone is unhealthy, then you need to be prepared to prove that all people are healthy. Does that make sense? I really hope it does make sense. This is something that you kind of have to just like practice on your own. Maybe take maybe just say something about something going on around you. and then try to put it in these quantifier symbols and negate it. This is something you gotta practice, but I think it's pretty interesting. So the last thing we're going to talk about is combining quantifiers. Now this, I'm not going to lie, this can be hard. This can be difficult to understand. Sometimes in proofs, there's a ton of quantifiers going on, and then there's negations occurring, and one little slip up can mean you end up proving something that's just irrelevant, right? So it can be really difficult. I'm going to try my best to make this less difficult for you. So I have two statements here. One of them is not true. If you can, try to pause for a second and guess which of these is false and which of these is true. Okay, spoiler alert. The first one is true, the second is false. Now let's look at this. So the first statement says, for all x, there exists a y such that x minus y is equal to 0. So what does that mean? It means that if somebody gives me some x, and let's say these are real numbers, I didn't specify that, sorry. Let's say actually, let's say they're integers because integers are nice. So somebody gives me an x, right? Somebody gives me some integer, then there exists a y. I can always find a y that will make the statement x minus y equals 0 true, right? If you tell me x is 3, then I'll tell you y is 3, right? If you tell me that x is 5, I'll tell you y is 5, right? That's just always going to work. So this statement is true. Now, what's wrong with our second statement? Because they're two very different statements. They look the same, but they're not. So the second statement says, there exists a y for all x such that x minus... Oh, sorry, I think I just read that wrong. So there exists an x for all y such that x minus y is equal to 0. What that's saying is that someone can choose an x, a singular x, that works for every choice of y. But that's not true in this statement, right? Say that somebody said x was 0. Well, if y is also 0, then it works. But if y is literally anything other than 0, like let's say 5, 0 minus 5 isn't 0. So this statement is false. I'm going to say this again because the difference between these two statements is minuscule and very hard to pick up on at first, but it matters. So the first statement says, for all x, you can choose a y where the statement is true. The second statement says, you can choose an x that will work for every single choice of y. So whenever you choose x, that is fixed for all y. In the first statement, you have more freedom to choose different y's. You know, if somebody gives you an x, you just choose a different y. For the second statement, once you choose an x, you're locked in. It better work for all y, right? So this statement is not true. Can we make it true somehow though, right? Is there a way we can? I'm going to change our operation from subtraction to multiplication, right? And I'll say xy is equal to 0. Now, this is true. Think about it for a second, think about why it might be, and then I'll say. So in this case, saying there exists an x for all choices of y, such that xy is equal to 0. And that's true. Why? I'll just say let x equal 0. Then no matter what y you choose, I don't care what it is, 0 times y is 0. So yeah, that's pretty much everything about quantifiers that we're going to go over today. I really find this stuff kind of cool, so hopefully you found it interesting. If you made it to the end of this video, thank you for watching. I really appreciate it, and I hope you learned something.